Lavrenty Gutsev is a computational chemist who has performed joint research with well-established researchers in a variety of fields such as photovoltaics, sensors, high-energy materials, catalysis, quantum dots, molecular magnetism, and semiconductor nucleation. He is particularly specialized in explaining experimental results via density functional theory and ab initio methods. With this introduction, I would like to invite him to begin his presentation. Thank you.
Thank you. Let me share my screen. Thank you, Dr. Matthews, for introducing me, and thanks a lot to Dr. Kumar for inviting me to this very exciting and interesting conference. Of course, there's always a lot of excitement and interest in these perovskite materials, which we hear so much about nowadays. And this research was this. Let me get the pointer. This research was done by a very distinguished and very talented group of experimentalists led by Dr. Troshin and a couple of pretty good theoretical guys, Dr. Mashandran Aldorshan, my boss, and me. As we say in Russia, if you don't compliment yourself, no one will. And this research was really done in very exotic conditions because really these perovskites have not been studied that much when irradiated by gamma rays. And you would expect them to, they're already not that stable in normal conditions, so you would not expect particular stability when irradiated by such powerful ionizing radiation. But this research was profound because we found some very interesting facts about these materials, and I think it's always good to start with the basics. It never hurts to start with the main goal of research, the overall aspect of what we're doing. So perovskites are great. They're great in terms of they have high power conversion efficiency, single junction power conversion efficiency. It's going up by year. They are, of course, relatively cheap and straightforward to manufacture, I'm told. And the problem, of course, the main problem that we're solving here is that they are unstable in normal operating conditions. They are unstable even under solar illumination, which is a huge problem for a photovoltaic cell, of course. So the issue is that even if we encapsulate them and engineer the interface, we still might not be able to fully stabilize them. Basically, the way I understand right now is one of the major issues with the material is that it is self-oxidizing. And here is an incredible result that the experimental group has achieved. So when we analyze this diagram they have, we have power conversion efficiency on the left hand side on the y-axis and the gamma ray dose on the x-axis. So when we start at the bottom, we expect cesium lead iodide to be more stable than methylammonium lead iodide, MAPI. But it's not. It degrades much more when irradiated by significant gamma ray doses. And again, when we look at bromide-based perovskites, again, they are even less stable when irradiated by this ionizing radiation. And that is, of course, a completely unexpected result. The other the other hybrid materials they degrade relatively quickly. But methylammonium lead iodide, in fact, did not degrade at all, because basically the way they did the experiment is this was done under glass, and when glass is irradiated, it darkens. And in space, the way they get around this is they use quartz, but here they use glass, and the glass darkens. So this red line is basically the expectation of how much the power conversion efficiency will decrease depending on the radiation dose. So as you can see, this can be attributed almost completely to the glass darkening. So the material under the glass has not degraded at all. And meanwhile, the bromide-based material degrades a lot. So there is something. So clearly, this is related to the iodine, and that's very surprising because of course we know that MAPI is typically not that stable a material. It's probably the least stable perovskite on average. So MAPI, as I said, it has a high radiation hardness. The open circuit voltage and fill factor do not change even after exposure to 1,000 kilorad. So this is basically space levels of gamma radiation. And again, we know that normally MAPI is not stable at all. So what do we think of when we see this? Well, we think of space, of course. We think of space-based applications because, as I will show you in a few slides, this material is actually not just hard towards radiation, it's actually self-healing when it's irradiated. And of course, a self-healing material in space where, doing any kind of repairs is very costly, much more costly than on Earth, is a huge win for the aerospace industry. So I had to explain with my theoretical colleagues why is it so hard towards radiation? Why is this perovskite so special? So first of all, let's just go over the facts. The fact is that we have a material that has a lot of charge neutral Schottky defects. This is well known. The most common Schottky defect that it has is the vacancy of methylammonium and iodide, very high concentration of that. But the thing is that these defects don't seem to really matter. The material is extremely tolerant towards defects. So the one thing that is probably responsible for this is that most of the defects are not deep traps, so they are not recombination centers. So the carrier diffusion length remains long because of this. But a secondary thing to note is that we see that, for example, interstitial iodine does have deep traps, two of them actually, one in alpha and one in the beta beta band. But the reason these are not a problem still is because when you do molecular dynamics calculations, you'll see that they start to fade in and out. This material is very plastic, and basically the way you can explain this is the electron-phonon coupling basically allows the carriers to escape these traps. So these traps exist, but they don't exist constantly. The fact that the material is so plastic actually removes them as they move. So the plasticity is a very important part of the defect tolerance of this material. The most mobile defect by far is the iodine vacancy. The barrier height is very low, maybe 0.2 EV. It's even lower if we choose a configuration where the methylammoniums are basically oriented as ferroelectrically or anti-ferroelectrically. In that case, it can be almost nothing. So if these defects are very highly mobile. And the last thing to say about defects in general is we have one defect that is very problematic. This is currently a hot topic of research, and that is hole-based oxidation of the material. So basically we create an interstitial iodine and a charged iodine vacancy, and this is called the charged Frankel defect. And the problem here, we believe, is actually these interstitial iodines. They migrate to the surface, and then they basically the surface degrades. That's basically what we believe is the issue with these. One of the biggest issues with these materials is that. So what do gamma rays do to the material? First of all, we have heavy elements in the material, right? Lead. So we have a high efficiency of gamma ray to free charge carrier conversion. This was studied recently, very recently, in fact. Our experimental group basically showed that the surface becomes iodine poor, but the bulk remains iodine rich. Now, the band edge. They also showed that the band edge. This suggests that the band edge carriers will dominate on the surface, and basically this equation is Fermi level pinning. So the methylammonium vacancy is pinned by the valence band edge carriers. So these are the positive carriers, and of course this increases as temperature increases. So this becomes more and more important as the material becomes hotter and hotter. So we'll have more of this pinning behavior with hot materials. Experiment previously showed that we have methyl, ammonia, and methyl iodine. They readily form in mass spec experiments, and of course mass spec is ionizing radiation, so that's something that we can look at to kind of figure it out. And of course, the main issue of methyl ammonium lead iodide is it separates into two phases: lead iodide and methyl ammonium iodide. And this one is the issue because this one of course is the one that can degrade to gaseous products. So what do we do? Well, simple. We just calculated the transition state barriers of creating these gaseous products. The barrier to make ammonia and methyl iodide is quite low, 2.5. And it's also a favorable reaction. You actually get energy out as you make it. Then we also have, of course, the reaction that creates hydroiodic acid. It's not as favorable, but when it becomes aqueous, so under exposure to water, it of course becomes more favorable. So this reaction is probably a very large issue for perovskites that are exposed to water. So what happens? Well, what happens is first in the gas phase. So first of all, we've gone through this reaction, right? We've gone through this reaction. We've gotten methyl iodide. It is cleaved. So as we know in mass spec, the heaviest atom is cleaved first. The weakest bond is cleaved first. Excuse me. The weakest bond is cleaved first. So the weakest bond is of course the iodine methyl bond. So that's cleaved first, and we
Lavrenty,
get an iodine radical.
Lavrenty, you have 4 minutes left.
Sorry?
You have 4 minutes. You have 4 minutes left.
Okay. Yep.
Thanks.
And the radical iodine can do a few things. It can favorably react with ammonia back, which can then favorably react with the methyl radical, and this restores the methyl ammonium iodide. And this is the key, basically. Basically, we restore the methyl ammonium iodide, and then the reaction basically starts moving backwards, right? The reason this reaction goes rightwards is because we're removing the methyl ammonium iodide, and that's basically what's driving the reaction to be just lead iodide, this product. And of course, we can also passivate the surface with the iodine. Most likely the surface will accept the iodine because it's carrier dominant. And we can form iodine too. It's not clear if this is good because the experiment shows that this is usually actually destructive. So maybe the explanation should be that iodine 2 can be cleaved by ionizing radiation, and thus we probably don't get this for very long. So this is the diagram. This is basically everything I have just told you. So first of all, we segregate into these two phases. We go for a transition state and we get ammonia and methyl iodide. Then our gamma radiation cleaves this methyl iodide further, and we get the iodine radical. Iodine radical can then either passivate the surface, or it can recombine with the ammonia, and then this radical can basically restore methyl iodide. And that is basically why methyl ammonium lead iodide is so unique, because it goes through this gas healing process, and actually the gamma radiation aids it in self-healing itself. And other perovskites simply do not go through this gas phase chemistry, and that is basically why this happens. So what's next? Well, first of all, we need to identify what's going on of I2. Why is this not a huge problem, or is it a problem? Is it the radical or the negatively charged iodine that's really important on the surface? And do we have redox chemistry going on the surface? So this is very exciting for space-based perovskites. The reason we have self-healing is because we have rich gas phase chemistry involving methyl ammonium and iodine, and the iodine radical is key to driving the reformation of methylammonium iodide and healing the surface back up. So I would like to thank my experimental colleague Pavel Troshin, because he does some very interesting, groundbreaking research. He's always at the forefront of this matter. He really got me into perovskites, and this has been quite an experience. Thank you for Dr. Ramachandran for helping me with the logistics and kind of guiding me towards doing this kind of theoretical research, and we hope to get more theoretical papers out and really get some deep insight on these materials. And of course my boss Sergei Mikhailovich Aldoshin for letting me work at IPCP in Chernogolovka. It's a very little cozy town. I really enjoyed it here. It's been a great experience working under him. Thanks, that's all, and I'll be accepting questions now.
Thank you. Are there questions from the panel?
Yeah, I have a question. Hi, this is Annalisa.
Mm-hmm.
Thank you for the talk. I have a question on your slide number 12 that I can see here about this summary of this reaction. So what are the characteristic time scales of this reaction that take place in usually?
That requires
from 1 to 6. Yeah.
That requires research. We know the barriers, but experimentally, I do not think any of this is yet known. This is basically a proposed model, and we basically it's just the theory that supports this at this moment. So this is very preliminary research. This is very recent research.
Okay. Okay. Thank you. Especially the first reaction. When you go to basically the separation of MAPi, do you have an estimation on that, or no?
Unfortunately, not yet. But that is clearly something that I've been thinking about. That also, that is something that we need to know. That is obviously a very important question. Yes.
Okay. Thank you, and thank you for the talk.
Thank you.
Lavrenty, I had one question. So. Over here, this mechanism is to explain the self-healing phenomena in MAPbI3 when you look at the gamma ray results, right? I mean, just to put it in perspective, right? But do you not think that this reformation can actually distort the lattice and therefore will also, I mean, although the material itself may eventually recover, the solar cell efficiencies may not recover because all these reactions would, have interfacial reactions with whatever material is sitting on top of it, etc. And I mean, I still have difficulty linking it to gas phase when the perovskite is a buried layer inside the solar cell.
Obviously, a lot of the gas phase chemistry that we're doing can also really be applied to interfacial chemistry. Whether it's an issue, so the surface, I feel like the surface is kind of the sacrifice. It seems like most of the efficiency remains in the bulk, not the surface. So what goes on the surface is basically to prevent a deeper degradation, because I think from what I've seen in experimental research is the depth of the degradation that is the issue. So basically the defects basically migrate opposite, right? We have a plus side and minus side in a cell, and basically the defects keep basically penetrating further and further. And in this case, what we can say is that the depth of the degradation is being limited, and I think that is basically the key to why this mechanism explains that the efficiency remains relatively high. That's my opinion on the matter.
All right, thank you. I think there are additional questions in the Q&A which I invite you to respond to. But I think we have come to the end of the first session on time. So Rakshith, I think you can guide us on